Hi everyone, welcome back. So for this video, we're going to discuss about stresses in beams. Okay, so before we go to the stresses in beams, let us have a short recap. So previously, we were able to discuss about the shear and moment diagram of a certain section. So for a certain section, we have here beam A to C, and we have a support at point B and a support at point D. And we have here our load diagram. And given that, we were able to determine our shear and moment diagram. So this shear and moment diagram represents the shear of a certain distance of that cross-sectional area. So for example, at here, at 9.665, if I am to cut my section at 9.665 and looking at the cross-sectional area, the shear here is 0. Okay, the shear is 0, but the moment at this cross-sectional is at maximum because the shear at the point of 0, the place of 0 shear is equivalent to the point of maximum moment. Okay, so given that, we are able to determine our shear force and our shear diagram, we will now be able to solve for the stresses that are caused by uh, this loading. Okay, so we have here two kinds of stresses on a traverse section. We have the normal stress that is caused by the bending moment, and we have the shear stress due to shear force. Okay, so for the normal stress, imagine we have here a beam. Okay, this beam, if we are to look close, okay, okay, so for example, imagine this is a beam. This ruler is a beam. That beam here, and I am to apply a downward force. So I am to replicate this beam as this ruler, and the loading will be applied. So look closely the deformation. Okay, so if we are to see that on the top view, it would look like this. Okay, if we are to exaggerate, it would look like this. If you are to observe closely, there is a normal stress happening at the beam. Okay, and going back to this figure, yun, na-exaggerate na natin yung beam, it looks like this. Okay, this is the neutral axis. The neutral axis is the point where it is neither compression nor tension. Now, if we are to look closely on our section here, sa taas nagkakaroon ng compression, while sa baba nagkakaroon ng tension. Naghihilaan sa baba, yung fibers sa baba naghihilaan, while yung fibers sa taas are compressing each other. Okay? We have the normal force sa taas as compression, and we have a normal force sa baba as compression, tension rather, and that is the one which is causing the bending moment. Okay? And that is what we are interested in solving for this chapter. That would be your normal stress, which is causing the bending moment. And number two, we are interested in solving the shear stress due to the shear force. Mag-shear off itong beam. Okay? And that is shear stress. Okay? If we are to look closely on our deformed shape, no, we are going to look closely on the fiber. You can see here at the top, ito, dito sa taas, it is compression. Nagko-compress. Nagko-compress yung ating fibers. The figure here on the right side is before the deformation. So you have here your Y, you have here your neutral axis that it is where it is neither compression nor tension. Okay. But after deformation, you can see that we were able to have a moment at a distance of rho from the point of, which is also our radius from our deformed surface. Now, given this, we can derive the strain to be negative y, this is negative y, divided by the rho. Okay? And having said that, we can say, we all know that the stress is equivalent to the modulus of elasticity times the strain. Okay? I repeat, the strain is equivalent to negative y over the rho, or the radius. And if we are to substitute that, the stress is equivalent to modulus of elasticity times the strain, or substituting, we have E times y over rho, and that is a negative equation. Okay, so looking closely, isn't it that stress is equivalent to pressure or force P? No, not pressure. Stress is equivalent to force P divided by the area. But this time, we have a changing force. So the change in force is equivalent to negative E times y over rho. This is the stress times the changing area. So this is what we are pertaining to. So the changing area is equivalent to the changing force. Yeah, so this is our changing area. So the change in force is equivalent to the stress times the change in area. And if we are to relate that with moment, because this normal force is the ones causing the moment, okay? So we can derive at our moment curve relationship. Moment is equivalent to E times I divided by the rho, or it is famously known as this equation. 1 over rho is equivalent to m over EI. Rho is the radius, m is moment, E is the modulus of elasticity, while I is the moment of inertia. Okay? So, if we are to substitute the expression of 1 over rho from the equation above, which is for the stress. Okay, so for the stress, we can derive our flexure formula as sigma is equivalent to negative moment times y over I. So the y here is the distance of the centroid of the area with respect to our neutral axis. So later on, we're going to appreciate this further as we have our example. Therefore, sigma max or stress max is equivalent to the maximum absolute moment times C over I. So C and I here are the same. Okay. But we have here S. What is S? S is the modulus of, no, it's the section modulus rather. S is the section modulus, and that is equivalent to I over C. So if you're going to look closely, you have here I and you have C at the numerator. But originally, it was I over C. And since it is in the denominator of the denominator, it will go to the numerator. So that is the section modulus. Okay. So here we have examples of cross-sectional areas that are commonly used in their section modulus. You don't need to memorize the section modulus as long as you know how to solve for your moment of inertia and to determine the distance c or the distance y with respect to the centroid. Okay? And we're now ready to solve for a problem. So we have here a problem, a simply supported beam supported at A, which is pin, and supported at E, which is a roller. It has a uniformly distributed load of 6 kilonewton per meter, and we have a point load of 15 kilonewton meter. So we need to compute for the maximum bending stress in the beam, sketch the bending stress distribution over which the maximum bending stress occurs, then compute the bending stress at a point on which section B is the 25 that is 25 mm below the top of the beam. Okay, so I redrew here the problem, and for this video we're no longer going to draw or derive our shear and moment diagram. So because we are already finished with that, but if you're still quite confused on how to do your shear and moment diagram, you can refer to our previous video. Okay, so we need to determine for this problem what is the maximum shear. Okay, so we should know that the maximum shear would always be present at the farthest fiber from the from the neutral axis. Okay, and at the neutral axis there will be no bending stress. So I repeat, at the maximum fiber from the neutral axis, it is where the maximum bending stress would occur. So we have here our working equation to be stress is equivalent to negative over I. Okay, but since we are dealing with the maximum and it is a symmetrical shape with respect to x-axis, we can use mc over I, where m here is absolute. Okay, so where do you think our maximum shear would our maximum moment would be occurring? So our maximum moment would be occurring at the point of zero shear, and that is 16 kilonewton meter. Okay, so we have here m max times c over I. Okay, so substituting the value, we have here, what is the maximum moment? The maximum moment is 16, and that is in kilonewton. So times 10 raised to 3, and that would be in newton. Okay, now what is C, or yung sinasabi nating Y? So C here is the distance of that fiber to the centroid or to the neutral axis, and this is what we call the C. And that distance from the neutral axis to the farthest fiber is 100 mm. So that is 0.1 meter divided by the I. I is moment of inertia. And the moment of inertia for a rectangle is I is equivalent to, write it here, we have bh cubed over 12. Okay, so from your statics of rigid bodies, diba? So sa previous subject natin, we were discussing about moment of inertia, polar moment of inertia. Yeah. So please be reminded of your formula for moment of inertia. Okay, so this would be the base, this would be the height. Then we can now substitute. So base is 0.12 times the height of 0.2 raised to the third power divided by 12. And that is equivalent to 20 times 10 raised to 6 pascals. Or that is simply equivalent to 20 megapascals. So this is the maximum shear. So since this is symmetrical, we can expect that the shear, the bending stress at the topmost fiber and that bottommost fiber is equivalent to 20 megapascals. So we are now ready to draw our shear and moment our stress diagram. So if this is the cross section of your beam, take note, like what I have said, if I am putting my load here downwards, this is the downwards, it is happening this way. And at the neutral axis, we have it is neither compression nor tension. So sa taas, it is compression. If you look closely, it is compression, and at the bottom it is tension. So our stress would look like this. So we have here the stress diagram. Okay, so we know that at the top it is a compressive stress. So please bear with the dogs. So we have here the compressive stress. Okay, since it is a compression, it is going towards the perpendicular distance of the cross-sectional area. Okay, and take note that this is our neutral axis. Okay, okay, so from the neutral axis down to the bottom, we know that it is tension. So more or less, this is how our stress diagram would look like. Okay, so it is tension. It is going away from the cross-sectional area. So this is how our diagram would look like. So this is 20 megapascals compression, and this is also 20 megapascals in tension. If you're going to see, it is a linear relationship wherein as we go nearer the neutral axis, the stress is becoming lesser. As we go far away from our neutral axis, our stress is increasing up to the point of the farthest fiber from the neutral axis. Then there we can get our maximum bending stress. Okay, so for part 3, according to the problem, we need to determine the bending stress 25 mm from the top beam. So if this is my beam, if this is the beam, this is my neutral axis, this is 25 from the top beam. Okay, so what is the stress at this point? Okay, take note that our working equation is equivalent to m c over I. And yung hinahanap nating moment is you have 0.8 meters from a support. So that is 0.8 meters, and what would that be? So by similar triangle, gagawin natin, we have 12 because we're going to subtract triangle. So triangle lang tayo. So we have 14 minus 2, that is 12. 12 is to the distance of 2 meters, while this portion is 1.2 is to the height of alpha x. And that is 7.2. But do not forget that we have an additional of 2 because this is a trapezoidal load. Therefore, that is equivalent to 9.2. So the height here or the shear here is 9.2. The shear 0.8 meters from a support is 9.2 kilonewtons. And the moment at that point is 9.28 kilonewtons. So we can solve the area here and we can get the moment here. And the moment is 9.28. So substituting that to our equation, we have 9.28 times 10 raised to 3 times c. So what is our value of c? So we have here the distance from the farthest fiber to our neutral axis to be 100 mm. So we subtract 25 mm from 100 mm, and that is 0.075 meters divided by the moment of inertia. Did our moment of inertia change? No. It is still 0.12 times 0.2 cube over 12. Therefore, our stress is equivalent to negative 8.70 times 10 raised to 6 pascals, or that is equivalent to 8.70 megapascals, and it is in compression. So negative, we can prove that the force here, the bending stress here at this section here is negative. It means that it is in compression. So if you are going to look closely, we can prove that it is compression. Okay?